Hello, everyone, and welcome to the summer semester at College of Western Idaho. Also, welcome to Physical Geology 101. If you signed up for Physical Geology this semester, then you are in the right place because this is the only Physical Geology lecture offered this summer. I am your instructor, Ryan McCutcheon, and if you ever need to reach me for any reason at all, please don't hesitate, and the best way to do so is through email. My email address is ryanmccutcheon@cwi.edu. I also like to host open office hours just about every week. However, I do have a separate full-time job as a hydrogeologist at Idaho Department of Water Resources, and so I'm not on campus very often. So my office hours are typically conducted remotely through Zoom. And if you haven't used Zoom, basically what I'll do is send out a link and post it on Blackboard every week. And all you have to do is click on the link, and then you can choose whether you want to join via just audio or audio and video, and ask any questions that you like. I'm going to start with my office hours being from 5:30 to 6:30 p.m. on Wednesday. However, I'm going to take a poll during the first week of class to see when most of you are available for office hours, and then change the date and time of my office hours accordingly. This course is a 4-credit course, and so the lecture, which I teach, has to be taken concurrently with the lab. I'm an online-only instructor this semester, so your lab instructor will probably be Jeffrey Larimer or Andrew Sundell, both of whom are very qualified to teach the lab. And the lab is in-person only, so that's something to note, is that you will have to go to campus twice a week to attend the lab. And without further ado, I'll get into a few more things that you'll need to know to succeed in this class, and then jump right into kind of an introduction to what geology is, and what this course is going to be about, so you can decide whether this course is right for you. All right, so now I'm going to go over some of the most common tools that you'll need to use in this course in order to be successful. And I define success in the class as learning a lot about geology and also getting a good grade, because as someone who is assigning quizzes and exams to evaluate your understanding of geology, I will do my best to make sure that if you get a good grade, then you learned a lot, and if you learned a lot, then you'll get a good grade, if that makes sense. So Blackboard will be kind of my primary platform for posting lecture materials, assignments, expectations, any announcements to changes in the course or upcoming events that you should be aware of, or that I would like to remind you of, even though those events may be listed in the syllabus. I like to give all of you reminders whenever possible. Speaking of the syllabus, it will be hosted in Blackboard. If you venture to the left side of the web page when you're on the Blackboard site for this class, there will be a link to the syllabus. And I highly encourage you to read the syllabus this week, because it has a pretty detailed list of my expectations, as well as what materials will be covered in this course. The breakdown of how you'll be evaluated and graded, etc. As far as the textbook for the class, it's the Essentials of Geology 13th edition by Luckins and Tarbuck. And you can pick it up in the bookstore as a hard copy. However, your tuition fees for this class actually pay for the e-text or the online textbook, as well as mastering geology software, which I'll get into in a minute. And I'll post an announcement on Blackboard in week 1 as far as how exactly you can access your online textbook and your mastering geology software. And the mastering geology software will be used for a number of assignments, probably just about every week. And what's really cool about mastering geology is it allows me to go beyond just asking you some bland questions about what you learned from the lecture or the textbook, and to actually allow you to kind of go on some remote geology field trips and evaluate geology as if you actually had an opportunity to travel to different places in the world and look at what's going on with the rocks and the soil and the water and the ice and the climate, etc. And then lastly, the lab manual, which you will need for the lab portion of this course, is the Physical Geology Lab Manual, 2nd edition, by Sundell, who is the full-time geology instructor at College of Western Idaho here. And you will need that because you'll be completing lab assignments every week in lab, and you won't be able to do that without the manual. And you can also pick that up at the bookstore. And I'm sure either Jeffrey Larimer or Andrew Sundell will tell you more about that when you first come to lab. All right, I swear I'm going to actually get into the lecture and start talking about geology eventually here. So just one more slide of some things that you should probably know and some context. This slide is basically about me, and it's not because I want attention. It's because I think that giving you some context for my education and my work experience and my life experience, etc., can inform you about the lens that I'm looking through when I'm speaking with you about geology. I am a scientist, and so I try to have as little bias as possible and to be as objective as I can when I'm presenting these materials or answering your questions. But the fact is that we can't avoid our own bias because our life experience does have an impact on our views. So I'm going to kind of share my background with you really quickly. As far as my education, I have a bachelor's in environmental geoscience from Slippery Rock University, which is a small university in rural western Pennsylvania. And while I was there, I primarily focused on hydrology and atmospheric science, I would say, although it was a pretty well-rounded education. And then I came to Boise State University and got a master's degree in hydrologic sciences from the Department of Geosciences. And so my primary focus was kind of the flow of water and the flux of water through natural systems. What does that mean? Surface water flow, groundwater flow, water quality, evaporation, and studying how all of the processes related to those fluxes and forces interact with one another. My work experience, I've had a lot of different jobs. So I spent about 1.5 years collectively working for the U.S. Department of Agricultural Research Service. And my time there was primarily focusing on how to eliminate invasive species like cheatgrass and medusa head and juniper in certain environments, and then restore kind of more natural native vegetation so that we have more properly functioning ecosystems that can actually host all of the animals that live in Idaho. And some of the field sites were also in like Oregon and Nevada and California as well. And then after I got my master's degree from Boise State, I moved to New Mexico for a little over 2 years and worked as a hydrologist for the U.S. Geological Survey. And there I was responsible for, or I was the project lead on an effort to kind of restore some ephemeral wetlands next to the Rio Grande River, as well as some natural habitat, and to also use those ephemeral wetlands to clean some of the runoff, some of the contaminated runoff from the city of Albuquerque before it made its way back into the Rio Grande. I worked on a lot of other projects there too, but I don't want to just talk about myself all day, so I'll move on. And then I moved back to Boise, and now I work for Idaho Department of Water Resources, and my primary focus is on recovery of the salmon runs. So I work with biologists and engineers who work on habitat restoration projects for Chinook and steelhead and sockeye. And I'm kind of their advisor from a hydrogeology perspective. So in what ways are surface water and groundwater and water quality related issues going to impact those recovery efforts is kind of my expertise in my current job. I also taught as an adjunct professor at College of Western Idaho for, I guess, cumulatively 3 years now, in the geology department and in the math department. And then I also taught at Boise State in the geology department, and I taught a class called Water in the West, as well as a number of labs. So I have a fair amount of teaching experience as well. As far as my philosophies, I'm not super focused on having all of you memorize a bunch of things. What's unfortunate about memorization is that for most people, when you leave the class, you're going to forget some of those vocabulary terms, and it's not going to have as much of a lasting impact on your view of the world as actually understanding the physical and chemical processes that are shaping the world around us might give you. And so my real hope is that what you'll get out of this class is you'll be able to go on a hike or drive down the road or get on your laptop and look at some satellite imagery or however you might view the outside world, and look at it in a different way where you can be like, oh wow, however long ago these rocks formed because a volcano erupted and then that lava solidified into rock. Or, oh wow, like this valley must have been carved over an extremely long period of time by this river. So those sorts of process-based learnings, I guess I would say, are what I'm most focused on teaching all of you while you're in this course. It's just to give you a new perspective on the world. Okay, so I'm probably over 10 minutes into this lecture entitled Intro to Geology, and I haven't told you what geology is yet. So as I alluded to earlier, I think it being the first week of this class, it's important for you to evaluate whether or not this is a course that you really want to take. I really don't want any of you to leave, but I also want you to be invested in learning if you do decide to stay in this class, so that you can get something out of it and get a good grade. So a lot of people think that, and for good reason I suppose, that geology is all about rocks. What are you going to get out of this class? You're going to learn all about rocks. You're going to learn what any rock is. You're going to be able to pick it up and say, this is granite or this is limestone or what have you. But the truth is that the field of geology is much, much broader than just rocks. You may have noted from the last slide when I talked to you about my background that, I have 2 degrees from departments of geosciences, and none of my jobs have been really closely related to rocks. Rocks are involved because they govern the way that water flows through natural systems, and they govern water quality. and they're involved in generating the soils that host different types of plants that I've studied. But it's not just rocks, and I think that's important to note. And we're actually in the process of changing the name of this department at College of Western Idaho from Geology Department to Geosciences, so that students understand that there's a lot more that you can study in this field than just rocks. Anyways, that was a bit of a rant. Geology, a quick Google search will show you that it is the science that deals with the Earth's physical structure and substance, its history, and the processes that act on it. So, given that definition, you can see that it's basically the study of the Earth, and not just the study of rocks. Although, as I said, studying rocks can help you to be better informed about the processes that act on Earth. Okay, so now that you theoretically understand what geology is, and so what the subject material for this course will entail, I'm going to talk about why anyone would care to study geology. So far I've talked a lot about how different Earth processes interact with one another, and that shapes the landscape in different ways and influences our resources in different ways, and that's all really interesting, but you might think, well, that's kind of nerdy. Who really cares? So one of the reasons why studying geology is important is that we all have Earth in common. You may have noticed that our civilization has slowly started to learn over the years that we can't just do whatever we want to this world without any consequences, right? So if you think that you can just dump an unlimited amount of waste into a river or a lake or the ocean and it's not going to have any impact, I think we've debunked that theory. Or if you pump a bunch of additional gases that used to be locked in rocks or fossil fuels into the atmosphere, you can change the concentration of those gases in the atmosphere, and then there's an impact from that. And the list goes on and on. And so understanding geological processes puts us in a position where we can, hopefully, as a civilization, collectively learn to live on this planet in a sustainable manner so that our children and children's children can continue to enjoy this place. And, outside of just sustainability issues, also in terms of the needs that we have for certain natural resources, the only reason why we know where those natural resources are or how to extract them is because we study geology. Geological hazards are another really important reason to study geology. So just for safety reasons. We're going to go over a number of different types of geological hazards in this class, and you'll come to understand more and more why having a basic understanding of geology helps us to protect ourselves from these hazards and to kind of forecast when these sorts of hazards might occur. So some good examples of geologic hazards that we'll be talking about are volcanic eruptions, like this one, some of which are way more explosive eruptions than others, and there are ways to predict the explosivity of a potential volcanic eruption. Flooding, like in this scenario. So there are ways to forecast potential flooding events ahead of time and also map out areas that are most likely to be flooded. And then you can see this confused gentleman in the background here, like, why is this giant boulder in my living room? And this is just, a less damaging example of mass wasting, which is when you have geologic materials moving downslope as a result of gravity and probably some sort of trigger like additional precipitation or snowmelt. So we'll talk about different types of mass wasting and how mass wasting impacts human infrastructure in this course. So another reason to study geology is that we all rely heavily on geological resources. And this is the case whether you live in an urban area or out in the middle of nowhere and simply rely on the land around you to survive. It's the case whether you're a big-time consumer that is using all sorts of electronics and eating out all the time and things like that, or kind of living a simple minimalist life. We still rely on geological resources to survive. So just a few examples of that are, mining rocks and minerals from the ground, which produce things as simple as a table, to mining copper, which is used to produce copper wire, which helps us to convey electricity from one location to another and pretty much power our modern society. We also mine fossil fuels, which we rely upon for our transportation, our heating systems, our plastics, and although, there may be someone in the class that doesn't use these things very often and is trying to live a very sustainable lifestyle, I think I would be hard-pressed to find anyone who has never used fossil fuels and who has never used copper or other sorts of resources that have been mined from the ground. And if you are someone that thinks that you meet that description, then I would love to talk to you, because it would be really interesting to hear about your lifestyle. Another reason to study geology is kind of hearkening back to how we all share this planet, and the human race has a rapidly expanding population. So we have over 7 billion people in the world now. And this chart that I just brought up shows the rate of population expansion. So you can see that in recent history, our population growth has been accelerating relative to the last few hundred years. And we're increasing in global population by over 70 million people a year. And having a greater population leads to a greater need for resources. Now, this can be counteracted to some extent by increases of efficiency of some of our systems and sustainable practices in our mining and agriculture and our lifestyles, but it's pretty hard to mitigate the impact of a rapidly expanding population just with those new technologies. And so at present, this expanding population means that the world, the human population of the world, needs more and more resources. And knowing where to head, not only where to get those resources, but also how to extract them in as sustainable of a manner as possible, relies on a good understanding of geology. So here you can see how this chart that shows the global energy consumption, including every different type of energy consumption that's commonly employed globally, mirrors the explosion of the human population quite well. So there's a pretty high correlation there, and although correlation does not equal causation, I think in this case, if you are to read some peer-reviewed journal articles about this, that you'll find that this correlation is largely caused by an expanding human population. So just to recap, as I said, I think this is the time for you to really evaluate whether you want to be in this course or not. Geology is the study of the earth, not just rocks. It's the study of all processes that influence the earth. And it's important to understand because we all live here and we all share Earth's natural resources. And so arriving at resource management decisions that both allow us to live enjoyable lives and are sustainable enough that we can sustain ourselves and future generations. Arriving at those management decisions is reliant upon an understanding of geology. And also, for safety reasons, understanding geologic hazards and the processes that lead to those hazards occurring and what sort of damage might be caused by such hazards is also reliant on an understanding of geology. And so this isn't like some abstract concept or something that's kind of unnecessary to understand. I think that really we need to understand geology to be responsible citizens of Earth, or at least to have a really basic understanding of Earth processes and, what's going to happen when we humans decide to modify the Earth in certain ways. So if that sounds interesting to you, then I think you should stick around. And if not, even though, like I said, I don't want you to leave, then perhaps you should reconsider. But with that, I will kind of start to dive a little bit more into what geology is and some of the foundational geological principles in the rest of this lecture. So stay tuned. So when I say that geology is essentially the study of Earth, that means that it's a form or a discipline of science. And so to understand how we arrived at the hypotheses and theories and conclusions that we've arrived at related to geological processes, it's important to discuss the nature of scientific inquiry itself and the scientific method. So it's important to keep in mind that science assumes that the natural world is consistent and predictable. This is important because if you have this assumption, then you can assume that looking at data from Earth's past can inform you about what might happen in Earth's future. And so the goal of science, and therefore also the goal of geosciences, is to discover patterns in nature and then to use that knowledge to make predictions about the future. And to do this, scientists and geologists collect data through observation and measurements, and then commonly use mathematical models that use that data as an input to predict what's going to happen in the future. Or in an even more basic sense, you can simply look at the data that has been recorded through observation or measurements, and then by analyzing that data statistically, you can determine how often certain types of geological processes are likely to occur again. So in science, how or why things happen are generally explained as a hypothesis or a theory. And it's really important to distinguish between these two because if you're reading someone's hypothesis, then it should sort of be taken with a grain of salt, or you should know that it is untested. It's just someone's explanation, or it's a tentative or untested explanation. A theory, on the other hand, is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. So a theory that you'll learn about in this class is the theory of plate tectonics. However, it's important to note that there was a theory that existed before the theory of plate tectonics that describes the way that continental plates move on the Earth's surface. And that theory was called the theory of continental drift. And they're different. So when the theory of continental drift existed, that was, our most widely accepted view within the scientific community. But it turned out to be wrong. So our theory is just sort of our best guess at the time that has been tested. So there's no real fixed path that scientists follow that leads to, more scientific knowledge or a better understanding of Earth, for example. So there's no fixed path that scientists use to go from a hypothesis to a theory. However, many scientific investigations or studies involve a question that is raised about the natural world, scientific data that are collected, and then one or more hypotheses are developed, and then experiments are developed to test those hypotheses. Usually those experiments use the scientific data that was collected as input data. Then those hypotheses are accepted, modified, or rejected based off of the analyses performed on the data that was collected. And then the data and results are shared with the scientific community. So if someone's hypothesis was accepted in their scientific study, and then a few thousand more scientists conducted similar tests, and their hypotheses were also accepted, and none of them were rejected, then you have a good candidate for a scientific theory rather than just a scientific hypothesis that was accepted. So this slide title is kind of a joke, but what I want you to get out of these slides on the nature of scientific inquiry and the definition of a hypothesis and a theory, etc., is that it's important in science to always be as objective as possible. And that requires that you remain skeptical, even if you feel like you've seen a lot of data or made a lot of observations that align with a certain scientific theory, because that theory could always be proven wrong in the future. And, perhaps you'll be the one to prove it wrong. So I like to think of science and geology specifically as it relates to this course as our best understanding of what's going on this planet based off of the information that we have today. But I also think that it's very important to remain skeptical and to continue asking questions, and to never assume that we have all the answers. And that's one of the reasons why I encourage all of you to ask as many questions as possible. Don't necessarily take my lecture material or the text material as gospel. You can take it as the author of the textbook's best understanding of what's happening, or my best understanding of what's happening. But I'm perfectly open to, new information that makes me realize that I was wrong, and I think it's important for you to be open to new information that proves you wrong or suggests that you might be wrong as well. And if you can do that, then you stand a chance at being a pretty good scientist, which is applicable to a lot of fields outside of geology. It's just kind of a philosophy you can carry into your everyday life that might make you less defensive about someone saying that you're wrong and more interested in just digging deeper to see if actually you're correct, or if maybe there might be some flaw in your thinking or understanding of whatever the topic may be. So moving back from, science as a whole to geology within the context of science, the nature of Earth has been a focus of study for people for centuries now. One idea that existed early on within the development of geology is known as catastrophism. And this was this idea that Earth's landscapes were shaped primarily by catastrophes. So, for example, someone who believed in catastrophism might look at the Grand Canyon and think, oh, wow, this canyon must have been carved out in some great catastrophe, some giant flood. One of the reasons for the existence of catastrophism is that a lot of people thought that Earth is only 6,000 years old, and therefore there wasn't a lot of time that had gone by to allow landscapes to be shaped slowly rather than rapidly. However, in the geology community and the scientific community, we look at the Earth as being billions of years old rather than 6,000 years old. So this understanding of a longer timeline that can occur to shape Earth's landscapes helps lead to a new idea in geology, which is called uniformitarianism. And this idea is just that the physical, chemical, and biologic laws that operate today have operated throughout the geologic past. So this uniformitarianism idea is kind of what I was talking about earlier when I was saying that, what's happened to the Earth in the past is the key to what's happening in the present, and the key to what may happen in the future. That is basically what uniformitarianism is. So with an understanding of uniformitarianism, one might look at the Grand Canyon and think, oh wow, this canyon must have been eroded over an extremely long period of time and, basically formed very slowly. So more about the development of geology. The Greeks were, one of the first people that we know of that there's written documentation of, them studying geology to better understand Earth. So some of the earlier thoughts by the Greeks were that, rocks were created under the influence of the stars, earthquakes and volcanoes are caused by escaping air in Earth heated by large central fires. And, these ideas might have seemed far-fetched to a lot of people at first, but they're actually not that far-fetched, which we'll learn throughout this course. They're a little bit off base, but they're on the right track, even back then. They thought that fossils were organisms living within Earth, which was an interesting thought. We'll explore later. But the important development within geology by the Greeks is that they were really the first to employ scientific thought. They were the first to sort of come up with hypotheses about what's happening on Earth and kind of devised ways to test those hypotheses, which was a big first step in the development of geology. So, sort of the next step in the development of geology was James Ussher, who basically used the Bible as a timeline for the history of Earth. And he took all of the generations that existed within the Bible and determined that if you subtract like the amount of time that all of those generations of people existed on Earth, that the Earth must have been created at 9 a.m. on Sunday, October 23rd in 4004 BC, or as I kind of alluded to earlier, 6,000 years ago. This idea was abandoned for about 200 years at one point, but it later had a resurgence in about 1925 as the idea for how old the Earth is. And, James Ussher really developed the idea of catastrophism. Or the idea of catastrophism sort of came from James Ussher's timeline. So he stated that, many previous worlds existed that were totally different from today, and the worlds were destroyed and preserved by catastrophic events, separated by periods of stability. So I think a big reason that those who believe in catastrophism thought surely the world's landscapes are shaped by primarily catastrophic events because, they believed that the world had only existed for 6,000 years. So there wasn't enough time to form crazy things like, Mount Everest and the Grand Canyon using, normal geological processes that we see in our everyday lives. So therefore, surely there must be major catastrophes that caused these things, was the idea. Continuing with the development of geology, this idea of catastrophism was eventually shown to be inconsistent. In other words, the idea that catastrophic events shaped all the landforms on Earth didn't make very much sense because no one could come up with ways in which certain landforms would be created through a catastrophe. For example, what sort of catastrophe would form Mount Everest? No one in history had ever observed any catastrophe that looked like it would form a mountain that looks like Mount Everest, for example. So this gave rise to a new idea in the world of geology called uniformitarianism. This idea really was the brainchild of James Hutton, who, because of how popular uniformitarianism is in geology today, is actually referred to by many as the godfather of geology. So the idea that he devised is basically that processes we observe today had been consistent throughout the geologic past, or that the present is key to the past, in other words. So if we go back to that, Grand Canyon study, for example, if we observe today, and this is not a true figure, it's just an example, that say the sandstone of the Grand Canyon was eroding away beneath the Colorado River at a rate of 1 inch per year. Well then, if we measure the depth of the Grand Canyon, we can get a ballpark estimate for how long it took for the Grand Canyon to form. If we say, for example, that, this canyon must have been eroding or forming at about 1 inch per year the entire time that it was being created. Which is much different from saying, there must have been a giant flood that no one witnessed or recorded that formed this canyon in one catastrophic event. So that would have been the old idea of catastrophism. However, the idea of uniformitarianism made people realize that Earth must actually be very old, because for enough time to go by for something like the Grand Canyon to form, for example, at the rate that it appears to be forming, or the rate of erosion that is making the canyon deeper, means that, Earth must have been around for much, much longer than 6,000 years to form many of the landforms that we see today. So that was a sort of like interesting side effect of this idea of uniformitarianism. So on to modern geology. As I said, geologists today still largely use uniformitarianism to inform their studies, and people across the world use it to inform their understanding of Earth. And also, some processes are catastrophic. Some landforms are formed by sort of quote unquote catastrophes. So catastrophism isn't, altogether false. It's just that not every landform was formed through catastrophism. We've had massive floods and massive volcanic eruptions and massive earthquakes that have reshaped the Earth in a dramatic way, basically immediately. But at the same time, uniformitarianism mostly holds true. So while all those catastrophes are happening, all of your baseline rates of erosion and deposition and formation of new rocks, etc., are still going on as well. Another example of a catastrophic event is a meteor impact. So this shows a picture of a meteor impact. Most of us have probably heard that 65 million years ago, a very large meteor impacted the Earth and may have impacted the survival of dinosaurs on Earth. So with this understanding in mind that uniformitarianism mostly holds true and catastrophism does occur and forms landforms rapidly, modern geology has come to understand that geologic time, or the amount of time that Earth has existed, involves millions and billions of years. There's landforms that weren't formed by catastrophes. There's no way to form them gradually without this much time passing by. And in fact, geologists have used geologic evidence, so basically the rate of radioactive decay of elements, to determine that Earth is approximately 4.6 billion years old, which is much different from 6,000 years and gives you a much different picture of Earth's history. And an appreciation of this age of the Earth is important when studying geology, because many processes are very gradual. So if you're using uniformitarianism to inform your understanding of geological processes, then you have to also reconcile that the Earth must be very old. So now that you understand how old Earth is and what implications that has on how landforms came to be and how Earth has changed over time, we should probably briefly discuss geologic time. So when I say geologic time, I use that term because normally when humans talk about time, we're talking about minutes, seconds, hours, days, weeks, months, years, decades, centuries, millennia even. But the geologic time scale is truly massive, because we're talking about a period of time of 4.6 billion years. So some geologists, in an attempt to simplify thinking about, the scope of 4.6 billion years, broke down geologic time into some categories. And these categories are divided into, and this is from the largest periods of time or categories to the smallest, eons, eras, periods, and epochs. So here on the far left of this chart, you can see eons of Archean, Proterozoic, and Phanerozoic. There's the word Precambrian next to Archean and Proterozoic eons there. It's because a lot of times people just refer to those eons collectively as the Precambrian. And this is because there was an explosion of new life forms in the Cambrian period, which is on the bottom right of this chart right here. And so I guess for a lot of people, the Precambrian period, but before 542 million years ago, was much less exciting. And then, so the periods that exist within the Phanerozoic eon, a lot of those are actually based off of changes in life forms on Earth. There were several mass extinction events during which life forms changed dramatically, and there were other major geologic events, like major volcanic eruptions that existed for millions of years and changed the amount of greenhouse gases in the atmosphere by orders of magnitude. So these different eras and periods are sort of ways to think about what was going on the Earth during that time without having to necessarily remember, 533.6 million years ago this happened. It's just no, it happened during the Cambrian. So I guess moving on from geologic time. So I'm going to let you read more about geologic time in your textbooks and move on to Earth as a system. So whenever I talk about Earth systems or geological systems, this slide sort of describes what I'm actually talking about. So if you conceptualize Earth as just a small, self-contained planet where everything on Earth is interacting with everything else on Earth, you can kind of conceptually divide Earth as a system into four different spheres. The first is the hydrosphere, which is the portion of Earth that is water. The second is the atmosphere, which is the gaseous envelope of Earth, or the gaseous portion of Earth that surrounds solid Earth. The geosphere is the solid Earth, so rocks, soil, some different things at the core of the Earth that we'll talk about later. And then the biosphere is all plant and animal life. And what's really interesting about the study of geology is that people don't only study these four spheres of Earth within the Earth system, but they also study the way that these spheres interact with one another. So let's take an example of this is let's look at the hydrosphere, for example. Since I'm a hydrogeologist, I'll talk about that briefly. So the water portion of the Earth, if you imagine a gaseous water molecule in the atmosphere, which is another sphere of the Earth, that gaseous water molecule might condense into liquid water while it's in the atmosphere, so then becoming part of the hydrosphere. And then it might rain or snow, and then that liquid water might fall down to the Earth's surface and then interact with the geosphere, the solid Earth. Then the liquid water might infiltrate into the soil, and then a plant or animal might use that water. So let's say a plant uses the water for photosynthesis, and then it transpires some of that liquid water back into the atmosphere as water vapor. So you can see that there are ways in which all four spheres of Earth are very connected with one another, and it's sort of an active and interesting study within geology, all of the ways in which these four different spheres interact with one another. So thinking of Earth as a system in these four different spheres, I think this is a really good photograph to conceptualize Earth as a system. So this photo was taken on Apollo 17 NASA mission in December 1972. And it's perhaps the first time that, the Earth had been called the blue marble, because when you look at Earth with the backdrop of the void of space behind it, you can see that it's all sort of one contained system in a way, or you can conceptualize Earth that way. And in this photograph, the dark blue ocean and the swirling cloud patterns remind us of the importance of the oceans and atmosphere in the ways in which the four spheres of Earth interact with one another, as I sort of explained earlier. So, as I've mentioned, Earth is a dynamic planet, meaning it changes all the time with many interacting parts or spheres. And when I say Earth is a system, just know that a system is a group of interacting parts that form a complex whole. So, Earth has four spheres that interact with one another, and within each sphere are a very wide variety of different things going on that form a complex whole, or an Earth system. So Earth system science specifically aims to study Earth as a system composed of numerous interacting parts, and employs an interdisciplinary approach to solve global environmental problems. So when I say employs an interdisciplinary approach, what I mean is, it's important to have people that understand physics, chemistry, hard rock geology, hydrogeology, atmospheric science, and all of these things, because only if we understand all of these different spheres of Earth well, and we understand how those spheres interact with one another, can we develop a good understanding of the Earth system as a whole. So now that you understand a little bit about Earth as a system and the four spheres within the Earth system, and how the Earth is basically just a blue marble in the middle of the great empty, let's talk about how Earth was formed and how it actually came to be the system in the blue marble that it is today. So scientists theorize that approximately 14 billion years ago there was a Big Bang, or a very large explosion, so to speak, that ejected hot hydrogen and helium atoms out into space. They were ejected from a very small, super condensed sort of focal point in the universe. And this was sort of the genesis of the modern universe as we know it. Now, after the Big Bang, as particles continued to expand or to move away from the Big Bang itself, particles began to cool. And as their energy states lowered, the molecular forces were able to act, and particles became attracted to one another and would start to combine with other particles. So this is sort of known as the nebula theory. And before I go into what the nebula theory is, we already talked about the difference between a theory and a hypothesis, but we should talk about the difference between a theory and a law. I'd like you guys to understand a hypothesis, a theory, and a law. So again, a theory is basically just a hypothesis that's been supported by years of repeated experimentation and evidence gathering where, that hypothesis has been accepted over and over again by a bunch of independent sources. But a law is really a widely accepted theory or a constant fact of nature. For example, the law of biogenesis is a good example of one. So a law is, you can think of it as even more concrete than a theory, and a hypothesis is less concrete than a theory. So moving on to the nebula theory, basically the idea is, after the Big Bang, all of these particles start to cool and become attracted to one another, and you end up with a rotating cloud of particles. And this is called a solar nebula. Within this cloud, particles continue to collide, building increasing mass, and the more mass you have, the greater the gravity you have, and then therefore the more additional particles you attract. Now, the rotational force, or the rotation of certain particles around other larger particles as a result of gravity, sort of causes all of the matter that's coming together to flatten into a disk shape as it's rotating, rather than a sphere. And as these particles continue to come together within this disk shape, you start to get sort of sections of the disk that are dominated by, one very large mass. And those came to become planetoids, which are basically just the precursor to planets like Earth. And in the center, you had that what everything was rotating around, all of that mass coming together came to form our sun, or in other solar systems, the star at the center of those solar systems. And then finally, these planetoids formed into our modern day planets as of about 4.56 billion years ago. So that is about how old Earth actually is. If you look at it from, looking at the physical Earth as being very similar to what it is today in terms of mass and shape, etc. I put a YouTube video on this slide. I'm not going to play it within this presentation, but I encourage you to watch it, and it gives a very cool explanation of the formation of Earth and the Big Bang and the nebula theory, etc. And I feel that they did a way better job of explaining it than I did, so please check it out. So after Earth formed about 4.56 billion years ago, it initially existed as a sort of cool temperature homogeneous sphere out in space. Not yet the blue marble though. So when I say homogeneous, I just mean that the composition was the same, basically the same in the center of the Earth as it was at the surface of the Earth, or rocks were made of the same thing, and most of the Earth was solid at this time because the temperature was cool. However, due to a relatively constant bombardment from matter within the solar nebula that formed Earth and other planets and our star, the Sun, as well as nuclear radiation creating a bunch of heat within the Earth, so basically radioactive decay of radioactive elements, the Earth got to a point where all of the solid began to cook and become a liquid, or magma. And at that time, iron and nickel, or the heavier elements within the Earth, started sinking towards the center, while lighter elements like silicon and oxygen started moving towards the surface of the Earth. And that is just due to gravity pulling harder on the heavier elements and less hard on the lighter elements. And that ultimately led to differentiation, which is when the Earth began to separate into distinct layers, leading to, having a core of iron and nickel, as you can see in this figure in the lower left here, and then the mantle, and then the crust. But we'll talk more about that later. The main point is that this is the point in time at which the Earth separated into distinct layers that had different chemical compositions, leading us to a more modern Earth. So, as I just mentioned, the metals like iron and nickel sank to the center of the Earth, and then molten rock rose to the surface of the Earth to create a primitive crust, or the outer layer of the Earth. And this differentiation, or chemical segregation, established the three basic divisions of Earth's interior, which are the crust, the mantle, and the core, as I mentioned. And then a primitive atmosphere evolved from volcanic gases. So some of the lighter elements exist in a gaseous form, and those came to the surface, and then Earth's gravity held those gases close to Earth, forming our first atmosphere. The earliest primitive crust that formed during this time was ultimately lost to erosion and geological processes because, after several billion years, all of the old primitive crust got replaced by newer crust, and I will explain how that happened in some later chapters, but it's maybe beyond the scope of this lecture. So I already talked a little bit about the three major layers of the Earth. If you're looking at the Earth, in terms of composition or what it's made of, those layers being the crust, mantle, and core. So you can think of the crust as really Earth's thin, rocky outer skin, so to speak, and the crust can be divided into the oceanic crust and the continental crust. The continental crust is what we live on. What we think of as land is continental crust. And it is usually 35 to 70 kilometers thick, and is composed of primarily granodiorite, which is a rock that I will explain the details of in greater detail later in this course. And then there's also the oceanic crust, which is much thinner than the continental crust. The continental crust is 5 to 10 times as thick as the oceanic crust. And the oceanic crust is composed primarily of basalt, which is a rock composed of heavier elements on average than granodiorite, which composes the continental crust. Oceanic crust exists beneath the world's oceans, as you might imagine. Then if we sort of journey down towards the center of the Earth, we have the mantle, which is 2,900 kilometers thick and is composed of peridotite. So peridotite is a rock that is composed of heavier elements than the rock in either the continental crust or oceanic crust. And this is because, if you remember, when the Earth heated up to the point where it was molten or liquid, that process of differentiation occurred and heavier elements sank towards the center of Earth, while lighter elements rose towards the surface. And then lastly, you have the core in the center of the Earth, which is composed of an iron-nickel alloy. So iron and nickel are two of the heaviest elements that exist in abundance in Earth, and so they sank to the center of the Earth. So again, this is a way to look at the Earth divided into 3 layers based off of composition, or what the Earth is made of within those layers. So you can also look at dividing the Earth into different layers based off of physical properties rather than just based off of composition. So again, composition, we're looking at the crust, then the mantle, and then the core, moving towards the center of the Earth. But if you divide the Earth by physical properties, then the outermost layer is called the lithosphere. And this consists of the crust and the upper mantle. And it all sort of behaves in a similar way, which we'll talk about more when we talk about plate tectonics. But when I say it behaves in a similar way, that's because its physical properties are similar. And then beneath the lithosphere, we have the asthenosphere, which is sort of a soft, weak layer below the lithosphere. The temperature and pressure of the rock in the asthenosphere is great enough that you can think of it as sort of liquidy or partially liquid. And you can also think of it as sort of a sea for plates or rigid pieces of the crust to float on top of, almost as if those pieces of the crust are like ships sailing on the sea. And then beneath the asthenosphere, we have the transition zone, which is a zone within Earth's internal, within Earth that is marked by a sharp increase in density, or the rock is much denser in the transition zone than it is in the asthenosphere, and therefore is not so soft and weak and liquidy, which is not the technical term, by the way. Continuing onward and moving towards the center of the Earth, and we arrive at the lower mantle. This is beneath the transition zone, and it's a zone of strong, very hot rocks that are subjected to gradual flow, or it means that they sort of move slowly in response to differences in temperature and density within the lower mantle itself. And then we have the outer core, which is a liquid outer layer of the core, and then the inner core, which is a solid inner layer of the core. The outer core and inner core are, composed of primarily iron and nickel, both of them, but their physical properties are different. One is liquid, the outer core, and one is solid, the inner core. because of the difference in pressure being applied to those materials, as some of those materials are closer to the center of the Earth, if that makes sense. So zooming in a bit to Earth's internal structure, as we just discussed, you can talk about the Earth's layers in terms of physical properties or in terms of chemical composition. So in this figure here, you can see the Earth's layers by physical properties on the left and the Earth's layers by chemical composition on the right. So examples of layers of Earth by physical properties are that the crust and the uppermost mantle together make the lithosphere. And then you have the asthenosphere directly beneath the lithosphere. And then you have the lower mantle, which is generally solid but can flow slowly. Then you have the outer core, which is liquid, and then the inner core, which is solid. And then layering by chemical composition, you have the crust on the outside or the surface of the Earth, which is a low density rock, and then the mantle, which is a high density rock, and then the core, which is just iron and nickel. So again, the only reason why I'm using different terms to describe these is whether I'm describing the layers of the Earth in terms of physical properties or chemical composition. So, speaking of the physical and chemical properties of the Earth, thus far I've mostly talked to you about where heavy elements exist within the Earth and light elements exist within the Earth. So, for example, heavier elements are usually closer to the center, lighter elements are closer to the surface. But anytime that the temperature and pressure conditions are right, those elements actually form into minerals, and those minerals form solid rocks. And so it's important to discuss rocks, what they are, what they're composed of, and the rock cycle, how rocks transform over time. So there are basically three major groups of rocks, and this is going to be integral to not only the lecture portion of this class, but also the lab, because you're going to learn to identify these different types of rocks. So the first type are igneous rocks, and these form from the cooling and solidification of magma, or molten rock. Also lava. Magma is molten rock beneath the Earth's surface, and lava is molten rock above Earth's surface. But anyways, examples of igneous rocks are a lot of the rocks that we talked about already in this lecture. So, for example, oceanic crust is composed of basalt, which is an igneous rock. Granodiorite, which is what the continental crust is primarily made of, is an igneous rock. And peridotite, which is what the mantle is primarily composed of, is an igneous rock as well. The second major type of rocks are sedimentary rocks. So these rocks form by cementing together a bunch of sediment, basically. So sediments are derived from weathering of pre-existing rocks. What makes sedimentary rocks interesting, I guess, is that the sediments in sedimentary rocks could be derived from weathering any type of pre-existing rocks. So they could have been igneous rocks, they could have been sedimentary rocks, or they could be rocks from our next major group that I'll discuss on the next slide. And then basically these sediments lithify, or another word for sort of solidify, into sedimentary rocks as a result of heat and pressure from being buried, and also from water flowing through the, what was originally unconsolidated sediment, and then leaving behind some sort of material that helps to cement the sediment together, or lithify the sediment together into sedimentary rocks. And these rocks often accumulate in layers at Earth's surface, because Earth's surface is constantly experiencing erosion of pre-existing rocks, and then deposition of that sediment, and then lithification of that sediment into new sedimentary rocks. So the last of the major three types of rocks I'm going to talk about in this lecture is metamorphic rocks. And these rocks form by changing pre-existing rocks. Those pre-existing rocks could be igneous rocks, sedimentary rocks, or they could be metamorphic rocks. So you can have a metamorphic rock that's exposed to heat and pressure, which is what causes the metamorphosis, and then it forms a new metamorphic rock that differs from what it was before. So looking at, now we have igneous rocks formed from magma or lava, sedimentary rocks formed from lithification of sediment, and then metamorphic rocks, which are formed from exposing any type of rock to heat and pressure and changing the rock. Well, with those three types of rocks, the rock cycle allows us to visualize the relationships between different parts of Earth's system, and to visualize why these rocks would change in their physical properties or chemical properties over time. So this slide just sort of zooms into the three rock groups a little more and shows you some real world examples of these three rock groups. So looking at igneous rocks, it's important to note that when molten rock solidifies at the surface, those rocks are called extrusive igneous rocks. So an example of that would be basalt, which forms the oceanic crust. And then if the molten rock solidifies beneath the surface, those are called intrusive igneous rocks. An example of that would be granodiorite, which is primarily what the continental crust is composed of. If you're wondering how you're hiking around and seeing granodiorite at the surface of the Earth, even though it is an intrusive igneous rock that solidified beneath the Earth's surface, it's just due to erosion. So as the Earth's surface gets eroded away, sometimes it exposes rocks that formed at one point deep within the Earth. So looking at sedimentary rocks, this photograph taken here is a photograph of the Navajo sandstone in southern Utah, which is a really famous sandstone because as you can see in the photograph, it captures sort of what was once a bunch of sand dunes. So you can see the tilt of the sand dunes that got solidified into sedimentary rocks. So it's a pretty cool snapshot of our geologic history. And then in the bottom photograph there in this figure, you can see some metamorphic rock. This particular metamorphic rock that you're looking at is called a schist, which we'll get into the different types of rocks later. But basically what happened to form this rock is that some type of rock got buried deep below Earth's surface, and then temperature and pressure reached a high enough point that it changed the physical properties and chemical composition of those rocks. So moving on to the rock cycle, I think that this is understanding, not only the different types of rocks and where they came from, but also the rock cycle is really key to changing your understanding of the world around you and being able to, as I said at the beginning of this lecture, sort of go on a hike and be like, oh, there must have been an ancient ocean here, or this rock must have formed deep beneath the Earth's surface in like hot and high pressure conditions. So I think it's a good way to start with this rock cycle here is to start in the upper left hand corner. So you can see magma or lava as part of the rock cycle, and then anytime that magma or lava, basically molten rock, cools or is put in conditions where it cools in temperature, then it crystallizes into igneous rocks. Now, the reason why when you look at an extrusive igneous rock like basalt and you can't see any individual crystals or any crystals of minerals is because it cooled on the surface and it cooled too quickly to allow time for the crystals to grow. On the other hand, when you look at something like granodiorite, which the continental crust is made out of, since that rock cooled beneath the Earth's surface, it cooled much more slowly, which gives time for the crystals of different minerals within the rock to grow, so you can actually see them. So in this rock cycle example, moving on from the igneous rocks, you can see if those igneous rocks are weathered or eroded away, then that forms sediment, and if that sediment is deposited and then buried beneath the Earth's surface, then it often gets compacted and then cemented together or lithified, forming sedimentary rocks. And then if those sedimentary rocks get buried deep within the Earth over time, as more and more sediment deposits on top of them, then it can lead to high temperatures and pressures that metamorphosize the sedimentary rock. So if you look at this picture of the metamorphic rock here, the sedimentary rock, you can see parallel layers like this, and then the metamorphic rock, the parallel layers got folded, and that is a result of the immense heat and pressure applied to those sedimentary rocks, and that's one of the ways in which metamorphic rocks change from their parent rock, or the rock that they formed from. And then the cycle starts all over again. So I would definitely take some time looking at this rock cycle and really thinking about it. Make sure, if you don't understand the 3 different types of rocks, or if you don't understand how the rock cycle works, to shoot me an email or stop into office hours or schedule an appointment with me to talk about it, because these are really important topics in this lecture. So now that you understand the rock cycle, it's important to talk about the face of the Earth, what it looks like today, and plate tectonics, the theory of plate tectonics. And this is because plate tectonics is actually, like, what happens as a result of plate tectonics is actually part of the rock cycle. And it's part of the reason why the face of the Earth looks the way that it does. And it's also responsible for some of the geologic hazards that we will discuss later in this class. So, as we kind of talked about earlier, continental crust and oceanic crust, the differences between the two. Basically, again, if you look at the continents, so the Americas, Africa, Eurasia, Australia, Antarctica, etc., that's continental crust. And most of the stuff in between that's covered with the oceans is oceanic crust. Okay, moving on. So the difference between these two areas, or the continental crust and the oceanic crust, is the relative levels. So obviously the continental crust is at a higher relative level or elevation than the oceanic crust, almost everywhere. And this elevation difference is a result of differences between density and thickness. So continents are relatively flat plateaus, approximately 0.8 kilometers above sea level on average. And as we talked about before, they're composed of granitic rocks. Granodiorite is a type of granitic rock. And the average depth of the ocean basins, which are composed of basaltic rocks or basalt, is about 3.8 kilometers below sea level. So this is because, as we talked about before, the oceanic crust is thinner and denser. So it's denser, so it's lower down in the Earth relative to the continental crust, and it's thinner, so it's much less likely to actually exist above sea level than the continental crust. So what are some of the features of the continents or the continental crust? Some of those features are mountain belts, and these are really the most prominent examples of features on the continents. So if you think of the Rocky Mountains, which we live in, the Andes in South America, the Alps in Asia, the Alps in Europe, the Himalayas in Asia, these are all examples of mountain belts. And then, as opposed to mountain belts, the cratons are sort of the stable interior of the continents. You can think of them as sort of the old continental crust that's been there for a long time. And within cratons, shields are expansive flat regions of deformed crystalline rocks. We'll talk about the Canadian Shield later in this class. And then stable flat platforms are the flat portions of cratons covered with a thin veneer of sedimentary rocks. So metamorphic rocks in the shields and sedimentary rocks in the stable platforms. So here are some examples of mountains within mountain belts and the North American continent mountain belt. Mountain belts tend to be relatively linear. We'll talk about why later. Linear meaning like kind of in a straight line. And the youngest mountain belts are generally more pronounced or have greater elevation changes within those mountain belts. And those younger mountain belts are less than 100 million years old and usually located on the edges of continents. Again, we'll talk about why later. Whereas older mountain belts are more subdued, not always on the margins of the continents anymore. An example of an older mountain belt would be the Appalachian Mountains in eastern North America, where I grew up. A lot of you Boise folks or Nampa folks might not even call what I grew up in mountains, but they're mountains to me. I guess it's a little subjective whether it's a mountain or a hill, right? Here are some more examples of mountain belts. The Himalayan mountains. Oh yeah, I should mention that the older mountain belts, the reason why they're more subdued or the mountains aren't nearly as large is because they've been exposed to erosion for a lot longer. So if mountains, just formed recently or are actively forming, then they might be a much higher elevation than mountains that formed a billion years ago and have sort of been exposed to a billion years of erosion. So moving to the more stable interiors or the cratons of the continents, they're usually, as I said, they're usually pretty old. So usually the rock is over a billion years old, and over time they're sort of worn flat from erosion. Within the cratons, the continental shield is where the rocks are exposed. So where they sort of like get eroded away more. And then the continental platform is where the rocks are covered by the sediment that got eroded off of the continental shield, if that makes sense. And as I mentioned, all together they form a craton, or the foundation of a continent. So this figure shows globally where some of these different features of continental crust exist. So you can see that the North American Cordillera is a young mountain belt, less than 100 million years old, which is why these mountains are pretty impressive. Same thing for the Andes and the Himalayas and the Alps. And then old mountain belts, you can see, as I explained earlier, the Appalachian Mountains in the eastern United States are an example of that. Continental shields, there's the Canadian Shield, which again I'll talk about in a little bit more detail later in this class. But there are major shields on all of the continents. And then the stable platforms also exist on all of the continents. So really every continent and every craton has mountain belts and continental shields and stable platforms. So, sort of on to the ocean floor and the features that exist there. They contain the continental margins. So the continental margins are the portion of the seafloor adjacent to major land masses. So, you know, on the west and east coast of North America, for example, the continental crust might extend beyond where we can see land a little bit further out, and it might be covered with seawater. That would be a continental margin. The continental shelf is the gently sloping region of the continental crust that extends off of the shore, so part of the continental margin. The continental slope is the relatively steep drop-off that extends from the continental shelf to the deep ocean floor. So this is sort of on the continental margin, moving away from where you can see land. Further out from the continental shelf is the continental slope. And then the continental rise is really a thick wedge of sediment that moved downward from the continental shelf and slope to accumulate on the sea floor. So it's basically where the sediment that's been eroded from the continental shelf and slope gets deposited out on the sea floor. So other than the continental margins, the seafloor also has deep ocean basins, and these are portions of the seafloor between the continental margins and the oceanic ridges, which we'll get to in a minute. These deep ocean basins have an abyssal plain, which is a flat feature of the deep ocean basin. And they have deep ocean trenches, which are deep and relatively narrow depressions that make up only a small portion of the sea floor. You may have heard of the Marianas Trench off of the west coast of the United States. That is an example of a deep ocean trench. They also host, deep ocean basins also host seamounts, which are small volcanic structures that dot the ocean floor, and ocean ridges, which are the most prominent features of the ocean floor. And they are composed of igneous rock that has been fractured and uplifted. So a good example of an oceanic ridge is the Mid-Atlantic Ridge off the east coast of the United States between the Americas and Europe. So we didn't really know a lot about the ocean floor until the 40s or 50s because it's pretty hard for a human to get down there. We need some advanced submarine technology, and we didn't develop sonar to be able to sort of image the seafloor until the 40s and 50s. So these are some diagrams sort of showing everything that I just described about the continental margin here. Kind of moving from the coastal plain out to the abyssal plain. And then this shows the slope, which is the steep edge of the continental material. In greater detail here. Kind of diving into the deep ocean basin a little bit more. So these mid-ocean ridges, like I said, the Mid-Atlantic Ridge is a good example, which you can see in this image here, are usually like extensive linear underwater mountain ranges. You can think of them as sort of seams on a baseball, and they kind of work their way around Earth. And we'll get into this more later, but what's going on at these linear underwater mountain ranges is these are actually areas where tectonic plates are spreading apart and magma is coming up from within the earth and forming new crust. Iceland, if anyone is interested in Iceland, is actually a unique example of seeing the mid-Atlantic ridge at the surface. So all the volcanic activity there is actually a result of being on the mid-Atlantic ridge itself. And here's sort of like zooming out. You can see how the mid-Atlantic ridge goes the whole way between the Americas and Africa and Asia here, for example. So that's all I have for you for the Intro to Geology lecture. I hope you enjoyed, and remember that I will also be lecturing on plate tectonics this week. Please also remember to watch for announcements on Blackboard so that you can make sure you're starting off the semester on the right foot. I want to make sure that everyone gets set up with mastering geology and understands where all of the educational materials and assignments are this week. That's kind of the most important thing, is to get you all up to speed and make sure that you understand the course structure so that you can get all the resources that you need to succeed. And lastly, I just want to say that Earth is an amazing place, and I'm happy to have you all here in this class. And I hope that you'll stick around to learn more about Earth with me. And also reach out regularly with any questions and start some interesting conversations so I can learn more as well. Hopefully I will talk to you soon. Thanks. Bye.